start.
I think we can
start.
start.
Yeah, I have admitted the participants. Sir, we are also going live on YouTube.
Oh, that's good. So I have to be careful.
So, we'll be sharing the YouTube link also with you.
Arun sir, also give right of sharing screen to sir.
I have already given, sir.
So now let's start.
Okay, let me share my screen.
So, sir, first Dr. Ankur will introduce you, and then I think you can share your screen.
Okay.
Yeah. He will formally welcome you, sir.
Thank you.
A very good afternoon to one and all present here. I, Dr. Ankur Chaudhary, along with my fellow organizing members, Dr. Arun Agrawal, Dr. Vishal Jain, Dr. Gaurav Raj, and Abhishek, welcome you all to this second session of FDP, which is themed on recent advancement in computer science and allied domain. I would also like to welcome our guest, Professor Jing Sing Yang from Middlesex University, UK. Professor Yang is from Middlesex University, UK. Friends, in last few sessions, we were on machine learning, deep learning, data analytics, IoT, and how to write good scientific articles. Keeping this in mind, today's session is quite interesting and addresses nature-inspired optimization, which covers all the domains. This session is very important for all those who are pursuing PhDs and are planning to pursue PhD as well as supervisors. Who could be better person than Professor Yang to address this topic? Let me now introduce Professor Yang to the audience. Professor Jingxi Yang is a reader in modeling and simulation at Middlesex University, UK. He is best known as a developer of various heuristic and meta-heuristic algorithms for engineering optimization. He obtained his Doctor of Philosophy in Applied Mathematics from Oxford University. He developed Firefly Algorithm in 2008, Cuckoo Search in 2009, Bat Algorithm in 2010, and Flower Pollination Algorithm in 2012. Firefly and Cuckoo search algorithm has become state-of-the-art algorithm since 2009, and more than 1,000, around I think 5,000 research papers cited Firefly and Cuckoo search algorithm. My dear friend, will you believe that he has more than 50,000 citations? His main interests are applied mathematics, algorithm development, computational intelligence, engineering optimization, mathematical modeling, optimization, and swarm intelligence. With this, may I request Professor Yang to kindly take over and address the audience. Over to you, sir.
Thank you very much. Let me share my screen. Thank you, Professor, for the kind introduction. Thank you for the organization. Thank you all for joining this session. It's really a pleasure to see you all, even online, not face-to-face. But after this, we will see you face-to-face in the future. But thank you for joining. The talk is very informal. I would suggest that this is, if you have any question, please feel free to ask. Or if you wish, you can ask at the end of this session. The idea is just to introduce some of the basic idea of a nature-inspired algorithm for optimization and computational intelligence. I do not assume you know all of this. I know many of you in the audience are expert in optimization, computer science, and nature-inspired optimization. But for this talk, I just assume you do not need to know anything. Right. in terms of the optimization, let's start with a simple story. Say, optimization is like treasure hunting. Imagine there's $1 million somewhere hidden in a forest. Suppose you wish to find it. If you can find it, it's yours. So what's your best strategy? But of course, you would say it depends on the location of the treasure. But the treasure is usually, it's an unknown target. It's somewhere in the domain, but we do not know its location. But imagine this, let me switch off my video so I can concentrate on the slide. So imagine this forest is very small. It's like a football pitch. So you can very quickly find the target without much effort. So what happens if the search domain is very large, like the Amazon jungle? So it's very large. It's impossible to do the search in one day or in 1 week or even 1 month. So the question is, what's the limitation? The limitation is, one, the search space is so vast, it's impossible to do every possible search of every inch of the space. So that's one limitation. The other limitation is, suppose even the search space is small, like say, suppose you have $1 million US in some of the building. Suppose they have a game show. If you find it with 1 hour, it's yours. Then the strategy will be different because you have a time limit. But if you have a lot of information about the possible location, your strategy will be different. Suppose in the audience, all of us, say 100 people, try to search this. If we find that we share it, then the strategy will be also different. So different strategy will affect the way we search. So that's why different algorithm will be different in terms of the search mechanism. So in terms of the optimization, we come back to this general formulation. Many things, many design need to be optimized. For example, we need to maximize efficiency, profit, performance, sustainability. And also, we may need to minimize the cost, the energy consumption, travel time, the carbon dioxide emission. So there's many things that we need to choose and also to try to reach maximization or minimization. But in general, we can formulate the problem in such a way it's in a way we can write all the objective or cost function as a set of functions. These are the objective. For example, the energy efficiency, when you do machine learning, the accuracy, the error, all this can be written as a set of a function vector. But in most cases, we only concern with one function. But there's a decision variable vector. So it's d-dimensional, which could be 2-dimensional, 200-dimensional, or maybe 2 million dimension. So it depends on the problem. But we just here give a general introduction. So you have a decision problem, you have to choose certain parameters so that you achieve optimality. So you have a cost function, say f of x, then you have some equality constraint and inequality constraint. Like suppose you design the engine, you have to fit into this certain size in terms of the car front or the back. So you have a dimension limit, but also many projects have a budget limit. So all this can be written as mathematical functions. In general, when we talk about optimization, we need to consider 4 different elements. The first thing is you have to formulate this optimization properly in such a way we have the standard form, which means it has a cost function, it has a lot of constraint. Typically, we divide into equality constraint and inequality constraints. Once we got that, we have to select an algorithm or sometimes a set of algorithms to solve this problem. But that's not enough. We also need to handle the constraint, say the equality and inequality constraints. And at the same time, once we implement this and handle the constraint properly, then we have to evaluate the cost function or objective function. Once we got all the information, we have to choose or select the solution based on whether if we try to minimize things, so whether the new cost function value is smaller than the previous one. And also at the same time, we should check whether the constraints are valid. If it's any of the constraint is violated, we have to consider this solution are not feasible. So then we have to do a lot of iteration. So that's why the computation cost is usually high. But despite a lot of the research effort in the last, say, 100 years or even longer than that, there's thousands of textbooks, and even probably each year there's several thousand of research papers published. But we can only solve probably 3 types of problems. I think there's a book called Convex Optimization, written by Professor Boyce in Stanford. He summarized all the different possible type of optimization problem. He indicated there's only 3 types of problem we can solve. One is the linear programming, which means the cost function or objective function is linear. All the constraints are linear. Then there's a very famous algorithm called simplex LP, simplex method. Then we can use that to solve this LP problem. Then the other type is convex optimization. A lot of problem can be rewritten in such a way it's convex. Then that book covered almost all the major methodology. So you can solve that type of problem and find the optimal solution. But the good thing is for convex optimization is any optimal solution you find is the optimal solution for the problem. So that's a good thing. But then the third type is the problem you can convert into the previous type. Everything else is difficult, which means there's a lot of problems are highly nonlinear. We cannot figure out a way to solve it. But of course, we still have to solve it in practice. That's why there is what are called the approximation method or the method specifically targeted to certain type of problem have been designed. But it comes back to a little bit of machine learning is many machine learning problems try to maximize the prediction accuracy. At the same time, is to minimize the prediction error and the learning error. But somehow they always try to formulate the problem as this mean squared error. It's a sum of the mean squared. So it's a convex function, but the domain is not convex. So the problem is not convex, and the dimension is very high. It's usually deep learning. There's several million or several dozens of million of weights to be determined. So it's a high dimension problem, but it's very hard. Right. Come back to the general idea of optimization algorithm. In general, we usually start with an educated guess. Suppose we have a solution we might know, but suppose we do not know. We usually start with a random point or vector in the search space. Then we treat that as the initial solution. We try to check whether this objective value is sufficiently small if for minimization problem. The maximization can be converted into minimization by say minimize the negative of the objective function. So now we will focus on the minimization. So you have one solution, you try to generate another solution. In a way, you wish to generate the solution in such a way, ideally the new solution should be sufficiently near the solution you are looking for. But we do not know the actual solution, optimal solution. So that's why it's just a random trial and error. Right, you were thinking, you mentioned that there's so many different algorithms in the literature. What's wrong with the traditional algorithm? The short answer is there's nothing wrong. Many algorithms like Newton-Raphson, they are very efficient. They can be tuned and implemented well. They can solve many problems very efficiently. The only minor problem is they are local search, which means that the final solution you can find will depend on the solution, the starting point, the initial solution you choose. Except, of course, for linear programming and the convex optimization. The good things for linear programming and the convex optimization, they are not dependent on the initial point or starting configuration. But the other thing is many of the old algorithms are approximation or problem specific, like the integer linear program problem, there's a branch and a bound. And like the traveling sales problem, there's the k-op. K could be 2 ops, 3 ops. So all these are depend on the type of problem. I think from the 1960s, in the last 50 or 60 years, people started to design problem and optimizer, try to solve the problem as the global search optimizer. So that's the new trend. Of course, it's more than 50 years, but in the last 30 years, people moved from the general global optimizer to the black box type, which is mainly nature inspired. That's my focus in the rest of the talk. Of course, there's so many different nature inspired algorithms. In general, there's initially called the evolutional algorithm, like the genetic algorithm in the 60s, and the evolution strategy in the 60s, and even evolution programming. Then in the 90s, there's a simulated annealing, which designed the algorithm in such a way it's based on the metal processing phenomena. But also there's a taboo search, which basically you trace the history, you try to record the history, then some of the parts you already went through, you should not go through that again. So that's why they have a taboo search. There's the called taboo list. Then in the 90s, there's anti-quality optimization, which is a major development, and also genetic programming. The other one is particle swarm optimization. I'm sure all of you heard of this particle swarm optimization. So then there's other algorithm like the differential evolution and artificial bee colony. The thing that we'll talk probably more here is the Firefly algorithm and the Cuckoo search and maybe the flower pollination algorithm and the bat algorithm. So there's a book. I could send a part of the book to you after the talk. It's called the Nature Inspired Optimization, and also there's some demo MATLAB codes I can send you. Right. Let's start with the basic one, the particle swarm harmonization. So think about how we deal with optimization problem. We have a problem, the search domain is vast. Then suppose we encode each of the solution as a vector. This vector is a high dimension vector in the mathematical space or the high dimensional hyperspace. So each point or solution is just a vector. But suppose the particle swarm optimization, what do they mean is each of the point corresponding to the location of a bird or fish swarming. But for the bird and fish system, why they swarm? There's many reasons, two major reasons. One is they swarm to find food and shelter. The other one is they have to swarm in such a way it's safe for the swarm. So there's a tendency the birds and the fish at the edge of the swarm try to move into the center of the swarm. So there's a center of gravity, that's called the G star. Then for each of the particle, it has a location xi. So the xi, that's a location. Then it moves with a velocity vi. Then each of the particle tended to move towards the center G star. At the same time, each of the particle have a historical best solution. When is the best, say the minimum solution they find. Then there's an updated equation. In this case, people usually ask why the unit is not right. They should have a delta t. Then the unit is correct. But because it's an iterational problem, so the delta t is 1, which means the first generation, second generation. So delta t is 1. So that's why we usually say, well, forget this delta t. We just keep as the x plus v, which physically is unrealistic, but mathematically it doesn't matter. It's just treated as a dimensionless quantity. Right, then once you have this formulation, what you can do? You are saying, well, let's do a little bit of programming to calculate what happens. So let's see. So you have a simple system. Can we rewrite as a dynamical system? I'll come back to this point later on. So for this particle swarm optimization, there's I don't know exactly the number, but at least there's more than 100,000 papers published about it. So there's a lot of research, but there are still two major issues. One is what is called the premature convergence, which means it can converge very quickly, but sometimes to not the global solution, but to the local solution or even wrong solution. That's one issue. The other issue is if the velocity is high, then we learned in physics the solution is what the energy is half mv squared. So the higher v means higher energy. The system may become unstable. In that case, we need to somehow limit the energy or the velocity. So that's why at least there's 20 different variants plus different minor variation. There's probably hundreds of minor variation. So one way to avoid that premature convergence is this. So we were thinking, what happens if we can avoid using velocity? So we basically get rid of velocity. So what's the philosophy behind that?
They've spent most of their brief lives as larvae, living in riverbeds.
This video is
But for
the
just a few weeks in summer, they
firefly
emerge
swarming
as
in the
adults
summer.
to find partners. The female flashes her abdomen to attract attention. Soon she's surrounded by eager males, all synchronizing their flashes with hers. People call this dancing swarm a firefly contest. They've caught the imagination of countless generations.
I tried to get one screenshot. Yeah, this one. So think about this photo. Is each of the parts is essentially a time lag photography. It's just for example, this is one of the firefly move around with this part. So the biology feature of the firefly, they have a different purpose. One of the reasons is to search for food or hunting. The other one is communication, to communicate with the other firefly. But think about in the vast empty sky in the summer tropical area, for the firefly, it's a very vast area. The search path is a very sparse. It's a single path for each of the firefly. But for a swarm of firefly, there are many different paths. We try to mimic this sparse path. That's what we should do. So we basically say we encode the location of a firefly as the vector xi. T is the current iteration. T equals 0, which means the beginning, or 1 as the starting point. So the update of the new location will depend on how the two fireflies, whether they are similar or their brightness. We encode the optimization landscape. For example, suppose maximization, we encode a higher value as higher brightness. If it's minimization, we encode the minimum value as a higher brightness. So then, because the light intensity vary with distance in terms of the inverse square law, but at the same time, the light will be absorbed in the air media with the exponential. We combine these two as E minus gamma Rij, which is the distance squared. Rij means the distance between the firefly xi and xj. So once we have done this formulation, that's the only single equation, then we can write it and do the simulation. So this is the PhD student in New Zealand. He did some simulation, use firefly. Basically, he traced each of the firefly during the search process. For example, this color means this firefly fly this path, but different color corresponding to different firefly. But also, even it's a similar color, that's different firefly, because it's basically display to show the path of the search of the different firefly are sparse. You can say it's like a tree-like structure or fractal-like structure. Right, let's do a little bit of simulation. So this is the Ackley function. It's a multimodal, highly nonlinear with one global minimum as 0, 0, 0. It's n-dimensional problem. But at the moment, we just focus on the two-dimensional problem. Then we start with initial Monte Carlo sampling. So the initial points are randomly seeded. So then gradually it becomes two simple swarm. One is at the global optimal 0, 0. The other one is there's a local swarm. But suppose we tune that parameter. That parameter is this gamma. Suppose this gamma equals 0. So this term is 1. This gamma is larger, this is smaller. If this gamma is it's tuned, say, suppose we say gamma is 0.5, then you see it starts with a random sampling, then quickly the whole swarm aggregated towards the global solution. So this is the behavior. It avoids that premature convergence, at least partially. And also, we do not use the velocity. So the energy is slightly much lower. Then, so the convergence rate is higher. So, right, of course, the example we have discussed earlier is it's really the only solution or global solution are at the in the center. What happens? Suppose the global solution are at the edge. Suppose in this scenario we have what are called holder table function. It has 4 equal optimal solution at the 4 almost the corners. Then we can do the same thing, but in this case we need a much more Firefly. In this case, I think it's I forgot, it's 150 or something. Then we similar this is so all the local mode can be found except 1 or 2. Then the global modes are here, this corner, and the other it's this corner. These 4 corners. So the idea is initially it's a single swarm. The Firefly swarm will be subdivided into multi-swarms, and each swarm will swarm around a local mode or optimal, or either maximum or minimum. Then among all the different modes, there should be some global optimal solutions. That's the main idea. Right, so that's one thing. So we improve the particle swarm in a different way. So we use a nonlinear system, avoid using velocity. So particle swarm is linear, Firefly algorithm is nonlinear. But there's a different way. The other way I'm discussing is the what's called scale-free search. Let me start with a video. So the Cuckoo search based on the Cuckoo behavior. There are 141 Cuckoo species. About 59 Cuckoo species engaging in the so-called reproduction parasitism strategy. What they mean is the Cuckoo species do not build their nest. They dump their egg or lay their egg in the other species like the warbler. So this is the cuckoo, this is the warbler. Let me play a video.
For the cuckoo's trickery to be successful, there is a lot she has to do. She must first remove 1 or more warbler egg to make room for her egg. She has to lay a similar looking egg so it's not recognized and thrown out. And she has to do this quickly so she doesn't alert the warblers.
I paused the let me make sure this went through.
Cuckoo chick has just hatched, and now the reed warblers have lost everything.
There seems a lag
Just
or something.
24 hours old and still naked and blind, the cuckoo chick instinctively pushes out any other
Let me
eggs in
play
the
this
nest.
again. I think
So
somehow
why is it
the video went through slowly. The audio went through faster. Let's see
For the
whether
cuckoo's trickery
I
to
can
be
solve this
successful,
problem.
there is a lot she has to do. She must first remove one or more warbler egg to make
The
room for her
eggs
egg.
laid by this cuckoo, there's 2 eggs laid by this cuckoo. In total, there are 3 eggs in this nest. 2 of
She
them
has to lay a similar
are
looking
the
egg,
cuckoos.
so it's not
It's
recognized and
very
thrown out.
difficult to
And
figure
she
out
has to do this
which
quickly,
is which.
so she doesn't alert the warblers. Cuckoo chick has just hatched, and now the reed warblers have lost everything. Just 24 hours old and still naked and blind, the cuckoo chick instinctively pushes out any other eggs in the nest. So why is it left to the newborn hatchling to take on? For the cuckoo's trickery to be successful, there is a lot she has to do.
Thank you. There seems some lag between the video I play here and the network. Basically, there are 3 eggs in this nest. 2 of the egg are the cuckoo's egg. So the question is, what's the strategy from the evolution point of view? The cuckoo somehow, this species never build their own nest. They lay their egg in the other nest. From the cuckoo's point of view, that's a minimum investment, a maximum gain. So that's the evolution for the species. But what happens to the warblers? If the warbler does not fight back, then the warbler species will die out. But somehow the warbler, of course, they will evolve and co-evolve with cuckoos. Then they will be able to identify the egg which may not be their own. So the strategy is this. So if the cuckoo egg was not identified, it will pass on to the next generation. And the cuckoo chick is hatched. And the first thing the cuckoo chick did was basically get rid of all the rest of egg. So it has a maximized resource, like food resource for the cuckoo itself, cuckoo chick itself. But if the warbler somehow did discover some of the egg are not their own, they will either get rid of them, so eat as a food source, or fly away to build a new nest, start from scratch without contamination. So the idea is we mimic this process by the 2 equations. The first equation is the similarity of the egg, the texture, the color are very similar. That's basically say when we do search, we should allow the solution are sufficiently different and also sufficiently similar. I always give this seems a silly comparison or analogy. Suppose you wanted to design an aircraft. If you start with the initial design from the shape of bird or fish, you need a less number of iteration to get the final design. If we start with the design, initial design as a table, then we try to modify. We need many iterations to get to the final design. So the solution should be sufficient similar, at the same time sufficiently different. So that's the idea. So the vector difference. Then PA is the discover probability. In nature is around a quarter or 1/3. So P can be 0.25 or 0.3. Then the other one is the new location, simply fly away. this is what called levy flight. Let me do a little bit of demo. So this function has a best solution at 1 and 1, but I took this log scale, so it's easier to see. But the idea is the same for 2-dimensional or 2000 dimensions. It's the same thing in terms of the idea how we program this. Then each of the new dot is a new solution. It seems it's not much clearer in this. It's just some dots or new solution jumping around. Let's see a different way. So suppose we look at this solution as a contour. The best solution should be at 1 and 1. Most time, I think around 84% of the time, the new solution is near this area. But occasionally there's some long jump like this one, or there's some long jump around 16%. This is the phenomena based on the scale-free or power law type of levy flight. If we enlarge this area will produce a similar behavior. Most time, the best solution will focus on the promising region 1 and 1. Occasionally, there's a long jump. So this type of search is the scale-free search. So what's the mathematical foundation or idea behind that? When we do the standard random walk, this should be random. I think that's a typo. It's isotropic random walk. It's a diffusion process. Think about you put a drop of ink in a tank of water. Then the molecule of the ink will start to move like a Brownian motion. Then that's the diffusion process. The average distance it moves will be proportional to square root of t. T is the shoot time or the number of iterations. So it's a slow process. The other process is called levy flight. It's called super diffusion. The mathematics behind that, that's a levy distribution, but we do not need to go to detail. We just say most time it's a local diffusion. Occasionally there's a long jump like this blue line. So this long jump means it can go to very far away from the original solution. If you do the calculation, the distance traveled is proportional to the t to the power 3 minus lambda over 2. Imagine lambda is 1. That's 3 minus 1 over 2. That's linear, which means t is distance is proportional to time. It's much faster than the square root of t. Of course, people do study such levy flight for many years. I think there's quite a few articles in Nature and Science. Researchers use mobile phone data and a lot of other data. Then they figure out many things move with potentially levy flight. Even light scattering is levy flight. For people, they say most time we stay at home or go to work, or go shopping, or go to the local park. It's more in a local movement. Occasionally, we take a flight to visit friends or relative or go to international conference. So there's some long distance movement. So if you fit this, you can get a power law type. So that's the search in terms of scale-free, which means it's a self-similar scale-free search behavior. That's the second type. So the first base compared to the first is linear, second is non-linear, the third one is scale-free. The one I wish to introduce is the better algorithm is it's the frequency tuning. Of course, sonar has been used in geological survey and many engineering applications for many years. But in terms of algorithm, that's what we try to mimic. Let's start with the better location echolocation.
The water bat chirps aren't exactly subtle. At 110 decibels, it makes more racket than a road drill. But like us, most of the insects it hunts can't hear ultrasound. As the bat homes in, its squeaks speed up. The water bat chirps up.
You got the idea from the video, because of course we cannot hear the echolocation of bats, otherwise it's very noisy. The BBC video basically tuned it down to the range we can hear. We noticed two very strongly features. One is the echolocation have somehow speed up, so the frequency is tuned up. That's one. The other one is the pulse emission. Each of the impulse, the rate of pulse emission is speed up or increased when the bat try to homing to at the target. So why they need to speed up the frequency? Think about what's the frequency is f. Suppose the wavelength is lambda. F times lambda should be equals to the velocity of the sound, which is 340 meter per second, 340. But that sound speed of sound is fixed. In order to reduce lambda, the frequency must be higher, because the resolution is typically a quarter of the lambda, which is the resolution. So reduce the lambda to a few millimeter, you need a higher frequency. So we mimic this. So typically the insect is a few millimeter, then they try to, the bats have to tune the frequency in such a way the lambda is in this range. Then we use this behavior. So frequently there's a minimum range, maximum range. We tune uniformly, but in real world it's not uniform. But then we use that velocity plus that location. Then at the same time, we speed up this pulse emission as a exponential increase is something like this. Because initially t equals 0, this is 0. T equals large is suppose infinity, this is 1. So the behavior is something like this. But this one, the loudness will decrease, then it's something like this way. So let's do a little bit simulation. So initially, all these particle or bats are randomly moving, then it will gradually towards this best solution at 0 and 0. So that's the idea. So compared to this previous 3 type, bat algorithm does not use linear or non-linear. Of course, this is a linear system, mainly linear system, But because this switching condition, it's weakly nonlinear. But the main idea is we use frequency tuning, which means when we search, we will decide should we go to local search or global search, depends on you tune the frequency. Of course, there's many other algorithms, like I mentioned, intercolony differential evolution, and flower pollination, and bee algorithm, and also mimetic algorithm. There's many more. There's 140 different algorithms. I think someone did a survey last year. So it's impossible to cover even in a book rather than the lecture. So I mentioned that there's some recent literature. I can send you some of the chapters. Right. Then the next question is, we would say, we have a lot of algorithms. We seem to try a lot of simulation and try to experimenting to see whether it works. Whether they do work or not, that's the main question. But surprisingly, from many thousands of research papers, they can work very well, and sometimes surprisingly well. Of course, I will not have time to go through many applications. I will quickly go through 10 different case studies. The first one is engineering design. There's like the dome design, tower design. In this case, the tower design have about 1,000 design variable. The constraint probably more than 4,000 constraint. The reason is at a different joint. How do you link one element with the other? The size must be about the same so that it can fit well. So for this type of engineering design, we wish to maintain structural integrity and safety, and but at the same time, we try to minimize the steel used, which means the less material cost, it's better. So we used the better element, we got the good results. The other type is what is called the reliability-based design. In engineering, there's many constraints. You try to figure out the feasibility first. Then you try in this feasible region, you try to figure out what's the best solution. So the feasibility is the most important one. Also the reliability. So we use the better algorithm, we got the good result. Then there's a lot of issue with deep learning. I think it's from our point of view, we try to see, can we use optimization algorithm to tune the hyperparameters? Because of the number of layer, many parameters, they were set in terms of either empirical value or the value you got from the published literature. So we try to tune them. In this case, we use better algorithm for the digital or the image application. And also the Brazil group also did what called the satellite imaging, trying to see from a satellite image to figure out the different crop types. Then this is the ground truth. Basically, that's the true solution. Then the other different algorithm try to see what's the solution they can produce. They used quite a few. Most of them can get about the same level of accuracy. And also there's a traveling salesman problem. Then we use the Cuckoo search. We got about 2/3 of the solution better or equally better than the published benchmark solution. The rest are equally good. And this is the research we carry out with one of the Indian research group is about the software testing, try to generate the independent testing paths. Because there's a lot of condition, then they use a combination of Firefly, and later on with the anti-colony, they got very good results. The other example is the feature selection. So in general, there's a lot of benchmark. In this case, that's the Brazilian group. They use the different methodology. Then we do not use any machine learning or data mining technique. We only use optimization technique. That's why the accuracy is much lower. It's about 60% without data mining. So this gives the good indication we should combine data mining machine learning technique with the optimization rather than purely use optimization. So again, this is the research with the Indian research group. It's the satellite imaging. For example, you have monsoon before that and after that. That could be certain area might be have been flooded. So you try to use this to estimate the potential damage. So they compared 14 different algorithms. I think they conclude Firefly use the least amount of computation time and get the most accuracy. Of course, the accuracy is not significantly different. It's from 80% to 81%, but the time saved is a lot. The other one is the research with the Spanish group, which is about the vehicle routing. Think about the vehicle deliver medical goods and newspapers. Then they have to collect the old newspaper and old medical goods to recycle or for simply destroyed safely. So they use the combination of mainly the Firefly with the different distance measure, like the Hamming distance, Manhattan distance, and also discretized, called discrete Firefly. They got a very good result with real traffic data. And finally, the example is with the Italian research group. One of the students, the research visiting research students in my group, then she did some simulation for the swarm of robots. The robot will not be controlled by any central location. It's no central control. All the decisions are made locally based on the local information. They use the combination of a Firefly algorithm with the anti-colony, trying to figure out, supposing a very large domain, there are several or many unknown targets, like a forest fire, chemical waste, or some even potentially a landmine, which people we want to discover to make it safely discomposed or destroyed, or somehow make sure it's safe. So the idea is a swarm of robots trying to find the unknown target with minimum time, but also consume the least amount of energy, because each robot have a fixed amount of energy or battery power. Then they maybe there's a charging station, but they have to enough power left to go to the next or the nearest charging station. Otherwise, they basically the robot is dead. So they did a simulation. They use a combination of Firefly with anti-colony. They got very good results. Right. I will spend the rest of the time to discuss mathematically how we can understand such behavior. So we know the algorithm, it's a data type. That's a different type of algorithm, and we know it may work well because we'll give you some example. But the question is, how do you analyze, understand this type of algorithm? But of course, there's many different ways to understand the algorithm. One is the qualitative understanding. Think about we analyze the components, velocity, and we analyze the stability, convergence, people usually draw the graph like this, say, well, there's initially then something like this. So you try to minimization problem. Or if the algorithm is good enough, it's something like this. Or sometimes it's even like this, which could cause a problem is premature convergence. But we do not want this type of algorithm, because initially start very, very slowly. It go to the solution much later. Ideally, we want something like this. So it started to search quickly, then gradually settle down. That's the type of algorithm we want. But of course, we will not be able to get this behavior if we do not understand the characteristic of this algorithm. So, of course, we can analyze different algorithms in terms of their components. So whether they use gradient like Newton-Raphson or not, most of the algorithm will not use a gradient, but the genetic algorithm use a crossover mutation. But most of the algorithm later on use mutation a lot, but plus occasionally crossover. Anytime which is to choose the best solution, it's always used. Right. What about the more quantitative analysis? One is to analyze the complexity, the computational complexity, and here is the number of population, or number of particle, number of bats, number of fireflies. T is the number of iteration. Most algorithms are the order of n times t, but we can use a different theory, like the dynamical system theory. I will come back to this in a few minutes. In the older numerical analysis, we use fixed point theory. Think about the Newton-Raphson. It's a fixed point iteration. I will discuss that maybe on the next slide. So there's many different ways in terms of the Markov chain theory, Bayesian framework. There's many things we can do. I think if you wish, I can send you some of the information of this book. Basically, we analyze briefly the different way of understand the algorithm from mathematical point of view, not in greater depth, but at least to certain depths. Right. The iteration, what I mean is, suppose you have an algorithm A. You start with some guess the solution x1. Then at any stage xk, the algorithm will depend on parameter alpha. Then you try to iterate. If the number of iterations large enough, ideally all this will converge into a fixed point. It's a fixed solution parameter, a fixed solution vector. So the dynamic system will come back shortly. There's a Bayesian framework. This is a very interesting idea. It's basically saying, initially we sample the search space using Monte Carlo. It's just the basic, almost the uniform sampling. That's the prior distribution. Then when we update, we use the new information gained or data obtained during the search, which means whether the objective value is smaller or larger compared to the old one. Then we update the new population, which should have a new distribution, which is called the posterior distribution, which should narrow down the parameter range. Right. Let's give me two examples. One is the what called the Markov chain theory. So what I mean is the Markov chain is there's some interesting characteristic. The first one is the next state will only depend on the current state and the transition probability. For example, tomorrow's weather will depend on today's weather and how the weather system like cloud, moves or pressure and the temperature moves change will affect tomorrow's weather. We will not consider the weather last week will be somehow fed into the future state, because of the weather, whatever happened last week and last month or even last year, we accumulated that information into the state, which is the today's weather, whether it's rain, cloudy, or sunny. So basically, the today is the state with all the information accumulated from the past. So we will not record history, only the current state and the transition property. That's the multi-chain property. That's one. The other one is if the chain run long enough, they will forget the initial state, which means in a year's time, the weather at any particular day will forget what happens today, whether it's whatever the weather today is. So that's the main two property. But of course, when we talk about the convergence, we are talking about probability sense, which means we can use this theory to prove, there's a paper in the book chapter about this, is we simplify the Cuckoo search, we can prove it will converge, but it's this kind of wording, almost surely converged, which means the convergence is almost surely. I noticed because of maybe the time lag or the internet lag, the audio is slightly ahead of that the laser pointer, which seems strange occasionally. Say when I say one thing, the pointer points another, but it's okay. So
It's
the
okay, sir, no
convergence is
worries.
not 100% guarantee, but it's almost surely means say 99% guaranteed something. Right, then the other example is a dynamical system. So we use this dynamical system, use the batch algorithm, we analyze its system property, we figure out the eigenvalue of this system. Then we calculate, use the Laplace, the Lyapunov stability criteria. Then we conclude the parameter should be in this triangular region. If it's an outside region, the algorithm may not be stable. If within this region, it's stable. Actually, we test to use a numerical simulation, we confirm the results. So we can understand the algorithm from the dynamical system point of view. Then most of the things we talk about now is, say we have a lot of algorithm. There's two extreme. One is called exploitation, which we use the gradient information. The other one is uniform search, which is almost random. Most of the algorithms are between these two extremes. You are thinking, what happens here? Anything interesting at the top corner? This is basically the what they call free lunch. Is there any free lunch? And the researchers in 1997 conclude there's no free lunch, which means it's very difficult to figure out an algorithm which is maximum exploitation, maximum exploration. It's impossible. But of course, in some the thing, the situation, free lunch is possible, like a co-evolution. The idea is this: when you train with, say, suppose you play tennis or play cricket, you trained with a better opponent, your skill will increase. If you train with a less skilled one, it may not improve much. So co-evolution could potentially produce better results. So in terms of the algorithm, it's potentially a better strategy. Before I finish, I wish to discuss 5 open questions. So let me make this slide larger so you can see this thing clearer. So the first one is, even we have a lot of different algorithms, even we can make sure it works in some of the scenario and solve many different problems. But we still have no idea exactly under what condition which algorithm will work. So we need unify the framework, mathematical framework, to understand the convergence, how quickly for a given algorithm to converge, the rate of converge. Basically, it's this way, or because there's a lag, so it's this way or this way. So it's we want to figure out a different way of our convergence. So, and also whether the algorithm is stable or not. So that's the one major problem we need to consider. Sorry. The good thing is there's not much progress, which means that there's an opportunity for new PhD students, even the master students, when you choose a topic, you can try to think about in this area, and also gradually you may choose to do a PhD in this area. So this is a good opportunity. The second one is parameter tuning. Many algorithms have parameters, and the parameter setting will affect the performance of the algorithm. For example, when I mentioned the Firefly algorithm, I have the gamma value either is 2, which we had 2 swarm in the end. Then gamma equals half, we got a single swarm. The convergence rate is different, which means the parameter will not only affect the performance, but directly affect the rate of convergence. So can we figure out how we tune the parameter? We can influence the behavior of a given algorithm. The short answer is we should be, but at the moment, nobody knows. All these tunes are based on empirical or parametric study, which means we know in this area, in this range, it should work. We did some experiment numerically, then it seems to work. If it doesn't work, we change the parameter range. So we need more. The other one is called parameter control, which means we do not need to fix the parameter, which means even we tune the parameter range, we do not need to fix them. We can vary it during iteration, which can be potentially better. That's why a lot of chaotic version, they put the chaos as a chaotic mapping as a replacement for the fixed parameter. The other one is benchmarking. This is purely for discussion. I mentioned that there's no free lunch, but then there's a lot of paper published. They compare, say, 10 algorithms, 20 benchmark functions. They conclude the ranking B is better than A, maybe H is better than B. Then this ranking process, I'm not sure how useful this kind of benchmark may be. The real world problem are very different from this benchmark. The benchmarks are usually smooth. The search domain are regular, typically unconstrained. Even it's constrained, but it's the constraints are very simple. Real world problem are always constrained, highly learning constraints, and the landscape may be highly multimodal, and the search domain may be very irregular. So even one can prove certain algorithm can work for benchmark function, there are no guarantee they will work for real world problem. So That's the way we should discuss. The other one is performance metric. This is very important when you select an algorithm. You say, I choose this set of algorithm, I say it works well. But this essentially depends on what's your criteria. Do you want accuracy? Do you want the speed? Or do you want, it depends on the metric. I use a silly example to compare, say, suppose in the Olympic, we run, we compare these 100-meter athlete, they run, say, under 10 seconds. If we compare them with the athlete for swimming and high jumping, it's not fair because their metric and the target is different. So the first question is, when you compare algorithm, what's the fair metric? Think about this. This is a very important question. Many paper use a different one, like the accuracy, successful rate. Is this good enough? So when you do a master research, a PhD, or when you do certain research, write a paper, when you decide to rank things, think about whether this metric is fair or reasonable. Finally, this problem is purely for future research. Is when we read the paper, we have a problem which usually is what's called toy problem. Toy problem, which means the dimension is usually a few parameter, a few dozen, very rarely a few hundred. Rarely you see more than 1,000. They seem to get a very good result. But the real world problem can be very large scale, several thousand, several million design parameter. The question is, can we simply scale up by using cloud computing, hypermodern computing, parallel computing? My impression is probably not. Then people say, what about the quantum computing? Well, all these things depend on the different way of thinking rather than simple use nature inspired. So to conclude, basically we say we can use nature inspired algorithm to do optimization and application, but we cannot expect that they can do much better than the traditional one in some case. So it's a combination of a new algorithm with the old one. That's probably work best. And finally, we have a book series called Spring Track in Nature-Inspired Computing. If you have a book idea or a conference, want to publish a post-conference, not a pre-conference, a post-conference publication related to the nature-inspired computing, computational intelligence, you're welcome to contact us. And finally, I leave this slide with some of the paper under the 3 book, which you might be interested in. Thank you for your time. Thank you.
Thank you, Professor. It was really informative, and optimally, I can say you have covered all the topics. You have given various open, challenging problem to the society, so that the various participants which are here, they can work on it and can take it as a PhD topic also. They can select it as a MTech thesis also, and they can work on it. You have beautifully covered all the approaches which you have developed and also compare it with the existing one. Really very beautifully, sir.
Thank you.
There are various great messages for you that it was really very informative session. Like I can read a few. Great, a very inspirational session. Thank you, Professor. So various messages we have. And one question also we have, I am reading it for you. My research work is on e-commerce logistic cost optimization by solving VRP using Swarm intelligence algorithm. Can you please suggest some ways to proceed with?
Thank you. That's a very good question. I think in terms of the solution to a problem, suppose you have a new problem. I think the best way is not to try the new algorithm first. Suppose you have a new problem, the first thing you should do is search the way to formulate the problem properly. Once you get the correct formulation or the formulation you trust, I think the first step is to use the traditional algorithm. Use all the traditional algorithm in the textbook or well implemented in the software. Try it. If it works well, that's it, because the problem solved. If it doesn't work or it's not ideal enough, then you try the new, slightly well-established, like the genetic algorithm, particle swarm, then try them. If they work better than the traditional one, then you can stop. You say the problem is solved. If in some unlikely case, they will not work, both the traditional one and the well-established one do not work, then you try the even more recent one, like the Firefly or any other swarm intelligence-based algorithm. Then if they work, then the problem solved. If all of them does not work, then it depends on the type of problem. Suppose you work for a company, for an airline, for a big research project, you have to give some answer, even it's approximate answer. Then in that case, I would suggest you combine swarm intelligence with the traditional algorithm, try to produce some approximate solution, which may not be globally optimal, but at least you produce some feasible good solution, let the decision maker to make a choice which one may be realistic enough to implement.
So we have one more question. For large data sets, which one is better, deep learning or nature-inspired optimization algorithm?
That's a very good question. The short answer is deep learning is better because the nature-inspired cannot be, at the moment, cannot compete with the well-established algorithm. There's many reasons. There's two reasons I can highlight. One is for deep learning, like the momentum or gradient-based method, like Adam optimizer, they can deal with a high-dimensional problem, maybe several thousand, several million, use the slow, tuned learning parameter gradually speed up. Then they can work very well. But for the nature-inspired, there's no testing. At least we haven't seen any test they can solve more than several thousand of design parameters. So it's mainly several hundred or several dozen. So there's no guarantee that will work for that scenario. But people started to combine the nature-inspired as the extra tool, an extra, alternative to combine with deep learning, data mining technique. That would be very useful. But we cannot rely on nature-inspired as the first choice. That's my impression.
Nice, sir. Sir, one question is from Abu Bakr Musha. He is asking that what does it make to be a member among your research group?
Sorry, could you say that again, please?
What does it take to be a member among your research groups?
Well, in the past, researchers can visit me if they have their own funding, or some of the PhD students have that exchange program, and also some visiting scholars. But because of the current situation, not much travel. Everything is online. Yep. So at the moment, I try. If anyone have any idea, we usually communicate online via email. Hope things will change. Thank you.
Yes, sir. Sir, one question is there that, sir, for large data sets, can CNN be used? I think it's yes.
I think that for large data set, I still want to emphasize we should use the combination of nature-inspired with the traditional data mining technique. That's very important. Yeah.
One more question. How deep learning and data analytics is useful to cope up with current pandemic situation?
Oh, that's a very good question. The short answer is no idea yet. But that's what this type of seminar or development program is very useful. It gave us not the way to solve problem, at least let us have time to think the new ways and the possible way to inspire a new way of thinking. So, of course, the choice should be always based on the old technique because it's well tested and also their mathematical foundation is clear. And also we have a lot of good implementation. We use that then in combination with swarm intelligence. For example, most of the older technique, when we produce solution, we usually start with one set of good educated guess solution when we move to produce better solution. If we combine, say, the idea with a swarm intelligence, we can say, let's produce many different initial possible suggested solution. Then each one is fed into in the traditional system. Then to see whether each different initial configuration can produce different one. Then we can compare and make a different choice. Ideally, it should be multi-objective. So we have a different choice we can make, depends on the preference of the objectives.
Sir, one more question is there. As nature-inspired approach growing day by day, what criteria need to apply when choosing its application in real world?
Oh, that's a very good question. So this is not just applied to the nature-inspired algorithm. Even the traditional one, we have many different types. I think the choice will depend on two things. One, the type of problem you are solving. If it's linear convex, no need to worry nature-inspired. Just use the traditional one. If it's a highly nonlinear, then we may need to think about the swarm intelligence or nature-inspired algorithm. But it also depends on the type of algorithm, because some algorithm can be more flexible. I think one of the flexibility I was thinking is this. Some algorithm, you need to tune the parameter very strictly before you can apply. Some algorithm, you can have a loose range. For example, in deep learning, the parameter value you can start with very small, say 0.0001, then increase. But for some algorithm, like in the Firefly, you can tune this slightly a narrow range. But for the Cuckoo search and differential evolution, you can have a slightly wider range. But I'm not sure for the particle swarm. If it's usually say people say 1, 2, but I think that the analysis has said there's a bifurcation point when the two parameter alpha plus beta equal 4. They will produce two different behavior depends on the parameter range. So it also depends on the problem. The third consideration will depend on your software availability. If one of software is already implemented, well tested in your research group, why bother to use the one nobody know how to implement? So also depends on the expertise of the group.
Sir, one more question. Nowadays, various major inspired approach have been developed. Around 200 approaches are available in the literature nowadays.
Yeah.
So when a new researcher comes to the market, it's become very difficult for them to select them which they should apply now, and day by day it is increasing. So what is your view on that?
That's a very good question. Actually, in this area, to be extremely frank, it's a bit a mess. It's quite a messy area because on the one hand, there's a lot of research which is good to exploring different ability, different area. But at the same time, it produces many algorithms which are extremely, in some cases, very similar to each other. So, and the performance could be varied. So it's difficult to make any choice. So I would suggest if you go into this area, so the best way is rather than choosing an album, it's probably try to think about all these kind of question which is not solved. Even you choose any album, like maybe I'm biased, say Firefly genetic algorithm particle swarm optimization. Can you at least do some of the analysis for genetic algorithm? There's already many analysis in terms of the convergence and
Yes.
rate of convergence. But what about the relative new algorithm? How to analyze their rate of convergence stability and the parameter tuning and this kind of thing, rather than develop new algorithm at all. The other things, even you have a motivation, you want to develop new algorithm, probably hybridization. Maybe select one or two algorithm, or two or three. Think about what's their advantage, why they may be very efficient under certain conditions. Can I extract the good things from each algorithm, somehow combine to produce a potentially even better one? But there's no guarantee the combination of the good components will give the good results. But you have to experiment it. So that's one way. The other way is try to see whether you can improve a certain algorithm. Even you say this algorithm, there's a lot of public say, can you improve them in terms at least two things, whether they can converge faster or they can produce more accurate results, even with the same number of function evaluation. So there's many things to think, but not necessarily just as simple to say, I wish to use this algorithm, I just want to produce a new algorithm. That's not the best way to proceed. It's just say, think about what you can contribute, especially for the new master and the PhD student. Then can you contribute in a different way so that it can really solve the problem rather than just philosophically say that's better. It's in essence, things you produce or contribute should be really a new contribution rather than try to say something simple.
Thank you, sir. So
Thank you.
rest, I am finding out the great messages. In the chat, regular, it is coming on the group also and the chat message also. So various great messages are there. Thank you so much, Professor. Such beautifully you have explored the whole area and you have given the problems to the PhD and UG as well as the PhD guides also, so they can work on it. Thank you so much. And
Thank
at
you.
last, I will also request you to be part of our upcoming conference. We will share you a uh, official invitation for that also. So we will be requesting you to be part of it.
Yeah,
Thank you
Dr.
so much.
Dr.
Yes.
Rankur, one thing was there in the chat section, as mentioned on the last slide, people are interested in knowing from where they can download the slides which can be used for teaching. Sir, can you go to the last slide? Yeah, slides
Yeah.
are available for teaching. So from where people can download these slides?
For this slide, I can send you to you. You can
Okay,
forward
okay.
to the audience. And also I can send you a few chapter of this book.
So
For
nice of
the,
you, sir. We will be very grateful to you, sir, if you could share with with us.
thank you. For the other slide, for the, I wrote, I think, 8 different slide chapter for teaching on each of the topic of this book, say, Firefly, Project Swarm. I can put online or maybe Google Drive, people can download that for
Yeah,
say a
that will be
fixed
very
period, say a
very
month or
beneficial,
something.
And
sir.
sir, I will
Yeah.
request your last journal name you have given. I have gone through that paper. I will request you to also give it, or I will download it and will share it to the participants because it is
Okay,
really
yeah.
nice. I have gone through that chapter. It is awesome.
Thank you, thank you.
So thank you so much. So with this,
Thank you
we
so
are
much, sir.
closing this session.
Thank
Thank
you.
you so much, sir. So participants, tomorrow again, we will be meeting in the next session. We will share that detailed with you on the group. Thank you so much, sir. Thank you, sir.
So thank you, and have a good early good night. We'll see you somewhere in the future, either
Sure, sure,
online or
sure.
face to face.
We request you to come to India now again after so
Okay,
many.
we will. Thank
Sure,
you.
sure.
Yeah.
Thank you
Thank
so
you
much.
so much, sir.
Thank
Have a
you.
great
Thank
day,
you.
sir. Have a great
Thank
day.
you.
Yeah.
Thank you.
Bye bye, sir.
Bye.
Bye bye, all the participants. Tomorrow's session will be at 2 p.m.